Hello, and welcome to the Chapter 17.2 lecture on line integrals. So, recall that the arc length of a function is given by the integral over a to b for the parameter t of the square root of the sum of the squares of the components, also known as the integral of the speed. And we'll have two definitions of the line integral of a function, the first of which is the scalar line integral. This one is the less commonly used one. It's a bit less useful, although still useful in some contexts. And what the scalar line integral of a function z equals f of xy is the area above your line on the xy plane and below that integral along your curved wall, so to speak. So if you were to take this wall and just make it straight and taut, then it would be the calc 2 integral of that. And how do we define this? Well, this area is the Riemann sum of the base times heights of these rectangles. Each base is your delta s, and then you have your height f of xy. So we want to take each delta s and multiply it by the height and add all of those together. Okay, but that delta s is exactly this. So all we do is we take our definition of the arc length and multiply the integrand by z equals f of xy, and we have our scalar line integral. So that's that. That guy is our ds, the same ds from here. Here's an example application. Here's a plate of radius 1 with a temperature distribution on that plate. And suppose that we want to find the average temperature on the rim of the plate. And suppose that this temperature distribution is given by t of xy is 100 times x squared plus 2y squared. So that's depicted here. It's the blue paraboloid. What is the average temperature on the rim? Well, recall that the average value of a function is 1 over the area of the base times the integral of that function over its region. This was because base times average height is the area or volume. So that means that the average height is the area over the base, i.e. 1 over the base. The area is the integral of the function. So what we're going to do is take the line integral over this circumference. That's going to be this integral, getting the total area, and then we'll divide that by 2 pi, which is the length of the base, and that will give us our average height, which is our average temperature along the rim. Okay, but to do that, we'll need a parameterization dt, and needing a parameterization will be a common theme throughout chapter 17. If we're not given one, we need to make one. So do you recall what the parameterization of the unit circle is? Well, there are many, but our canonical one, it is cosine t sine t. That's the x component, y component. And that's for t between 0 and 2 pi. Okay, and we'll need our speed. You may recall that this was actually an arc length parameterization, but we can compute that speed by taking the square root of the squares of the derivatives, and that is 1. And the area of the base of the line integral, i.e. the length of c, is 2 pi. It's just the circumference. So our average temperature, the average value of the function, is the integral from 0 to 2 pi of f of xy times 1 dt, where this guy is our ds, the same ds is there, and this guy is our f of xy as there. And we have our bounds. Okay, but wait, there's a problem here. We have an x squared and y squared, we're integrating it dt. So what we need to do is we need to get this into t's only. How do we do that? Well, remember that this is x and this is y in our parameterization. So what we do is we just replace this x with cosine t, replace the y with sine t, and then we have an integral in terms of t onlys, dt. And doing that replacement, we wind up with this. And one can then evaluate that and get 300 pi. Oh, and recall that we also divided by 2 pi. So all of these are divided by 2 pi. That was to find the average temperature after all. So our final answer for the average temperature is 150. All right, so that's scalar line integrals. We can also do scalar line integrals in 3 dimensions. Consider the integral over the curve C of z ds, where C is this helix between time t equals 0 and t equals 2 pi. So that's one revolution around this helix. Okay, so we already have our parameterization of C, and this integral will be the integral from 0 to 2 pi, the bounds on our parameter, z times r prime of t dt. So we need to find r prime of t and find its magnitude. R prime of t is the square root of the sum of the squares of the derivatives of the components. We computed this for the same example earlier in the class, and one ends up getting root 3 squared plus 4 squared is 5. Okay, so this is 5, and z is 4t, and then it becomes a relatively simple Calc 1 integral. So we wind up with just the integral from 0 to 2 pi of 4t times 5 dt. And computing that integral, we have 40 pi squared. So that's scalar line integrals. However, there is another type of integral that is much more powerful and common, and which will be the focus of the rest of the class, which is the line integral of a vector field. And when people say the word line integral or path integral, this is what they usually mean. So vector fields, as we know, are ubiquitous in nature, and we frequently want to tabulate the total amount a particle goes against or into a vector field as it moves through space. If the vector field is force, then that will give the total work done, force times distance. This we call a line integral or path integral of the vector field, and let's see a visualization of it. So we're going to move through this vector field, beginning here, and as we move through it, then we compute the projection of the vectors onto our direction of motion, and that projection is the dot product. So the integral along our curve C of the vectors, vector field dot dr, that's our path integral. Let's see the visualization again, and down here will be displayed that projection. So there is our force vector. We take the projection onto our r prime, our direction of motion, as that dot product, and this is the dot product at various places as we go through. And then the integral of this function down here, that integral of that is our path integral of the vector field. I'll let it play one more time. Yep, there. Pretty cool visualization. So we define the line integral or path integral of a vector field f along a curve C. to be this, f dot dr. And as with scalar line integrals, that dr is r prime of t dt, because dr dt is r prime by definition. So we'll convert everything to be in terms of our parameterization this way to actually compute it. And note that TDS, where t is that unit tangent vector, is dr. The reason is up here. So t, by definition, was r prime over the magnitude of r prime. Recall that. Multiply both sides by the magnitude of r prime, that's the speed. And then write out that r prime is by definition dr dt. And the speed, remember, is ds dt. Multiply both sides by dt, and we get the differential dr is t ds. And f dot tds is velocity invariant. It's an arc length parameterization. So no matter what velocity we move along the curve with, we end up getting the same path integral. So in other words, it's parameterization invariant. One way to think about that is that if we, for example, move along this twice as fast, then we do it in half the time. So sure, moving along at twice as fast, our drs will be twice as long, but we do it in half the time, so it compensates for the dot products being twice as big, and you end up getting the same result. So that's a good way to think about it. And that's why the dot product is sufficient for the projection, because f dot t is magnitude of f, magnitude of t cosine theta. However, t is a unit vector, so its magnitude is 1. You don't even have to write it. So that dot product is directly the projection onto the direction of motion. And work, as we know, is force times distance. So the total work done is the integral of force dot t ds, because we want to take the component of force in the direction that we're moving. That's the little distance that we're moving. And this is our path integral of the vector field along that curve. So in other words, the path integral through a force field, meaning a field of force vectors, is the work necessary to move a particle along that path through the force field. So let's do an example. Here's our first example of computing the path integral of a vector function. Suppose the force on a charged particle at position x, y, z exerted by an electromagnetic field is F is negative y, negative x, negative 2z. And the particle moves through the path, r of t is 1t t squared, for t between 0 and 1. Calculate the work done. Okay, so our path integral is this along the curve C. We're parameterizing, that'll be 0 to 1 of f dot r prime of t dt. Due to this, that's always what we do to actually calculate it. Let's write some things out. Okay, so r prime of t, that is 0, 1, 2t. It's just the derivative of this. And f, we need to get it in terms of t. That is negative t, negative 1, negative 2t squared. That's because r of t was this, so at a given position, that's our x, y, and z. So we plug those in for our x, y, and z. That negative y there is a negative t, for example. Okay, so our path integral is the integral of negative t, negative 1, negative 2t squared, dot 0, 1, 2t dt between 0 and 1. Okay, and to be clear, this is our f of x, y, z from here, and we're substituting our x, y, and z from our path there. So now we compute this dot product, and we have this, writing it out manually. We take the sum of the products of the components. We have the integral of negative 1 minus 4t cubed Integral of that is negative t. Integral of negative 4t cubed is negative t to the fourth. Between 0 and 1 is negative 2. So our work done is negative 2. In practice, that might mean something like instead of pushing it, you're trying to hold back a dog running. That'd be negative work in which the force vector is on average going in the opposite direction of the direction of motion. Now, a special type of path integral is a path integral along a closed curve. Remember that a closed curve is a curve that has no beginning or end. It loops back and meets itself. So this would be a closed curve. It doesn't have to be a circle. It can look like this. This would also be a closed curve. On the other hand, this would be an open curve. That's open. This guy is closed. And a path integral along an oriented closed curve of a vector field is called the circulation of f on that closed curve. And what the circulation computes is the total contribution of the vector field in the direction of the oriented closed curve. So here, with this counterclockwise orientation, we would have a positive circulation resulting from this vector field. Whereas over here, with this counterclockwise orientation, the circulation would be 0 because this vector field has no contribution going either left or right at any point. Okay, well, to be clear, over here, it contributes in the direction of the closed curve at all points, really. Later, we'll get into what circulation really is. It's strongly related to how quickly a little wind turbine at this point would be spinning. So over here, a wind turbine would not be spinning at all because the vector field, if we imagine it like wind currents, is not going either left or right along our turbine that might have, well, turbines that look like this. Whereas over here, our turbine would be spinning this way from that circulation. Let's do an example. Let's compute the circulation of the vector field negative y comma x along the unit circle. And by the way, negative y comma x, that's a vector field that we looked at earlier. It looks very much like this. So what we should expect as we move along the unit circle with our standard parameterization counterclockwise is a positive circulation from this vector field. Let's compute what it is. Okay, so we want f dot dr, and with our parameterization, what are the bounds on t here for one complete revolution? Well, t is between 0 and 2 pi. So we should have the integral from 0 to 2 pi of f dot, okay, dr. We replace that with r prime t dt. F is negative y comma x. R prime is negative sine t comma cosine t. And then we have our dt. Okay, very well, so that's our f. However, we want an integral with only t in it. So we want to get this with t's only. And to do that, at any point t in our parameterization, this is our x and that's our y. So we just replace y here with sine t and replace x with cosine t. Okay, so that's our y, that's our x. And now we take this dot product and it becomes a calculus 1 integral. So we have the integral from 0 to 2 pi. Negative sine t times negative sine t is positive sine squared t. We have a cosine t times cosine t. And we have our usual Pythagorean identity that's equal to 1. And the integral from 0 to 2 pi of 1 is 2 pi. Okay, so we got a positive circulation as we would expect. And in as much as the circumference is 2 pi, we can think of this as like it contributed a uniform contribution of 1 across the circumference of 2 pi. And circulation can also exist in 3 dimensions. And it's with exactly the same definition. It's just that our dot product involves 3 different components, but it's no different in principle or early computation. Now, for our next concept, which will be another fundamental concept of chapter 17, we'll want to recall the scalar projection. So this is a slide from way back then. Recall that the projection of u onto v, that's u dot v over v dot v times v. And recall that b dot v, this is the magnitude of v squared. We can break that up as magnitude of v times magnitude of v. So we have this. It's the same as this. And this guy here is called the scalar component of u in the direction of v, because it's the magnitude of the unit vector that's facing in the desired direction, with a minus sign if the angle between the 2 vectors was obtuse. And note that if n is a unit vector, this will be a normal vector to a curve, then the scalar component of a vector f in the direction of n, plugging in, it would be f dot n over the magnitude of n, but if n is of unit length, that magnitude is 1, so we just have f dot n. We'll be using this right here. So the circulation is the total contribution of the vector field in the direction of the closed curve. And we'll also want the total contribution of the vector field orthogonal to the closed curve. This will be like the wind cross current through the curve. Okay, and to find that, take a look at this part over here. I think it's easier to visualize here. We have our vector, and what we want to do is project it onto the normal vector n, which will make up unit length. And then that projection of f onto n will be the component of f that is orthogonal to the curve there. It's like if this were a velocity vector of wind, it would be the component of wind that is orthogonal to the curve, which is the cross current through the curve. And the other component is the component of wind that's moving with the curve. And what we want to do is project f onto n, take the magnitude of that, and integrate that. Well, the magnitude of the projection of f onto n is the scalar projection. And we already found that that is f dot n. Oh, and if f is facing inward, then that angle is obtuse. And that means that the scalar component of the projection would be negative, and that negativity corresponds to that then the flow is moving into the region inside the curve rather than out of the region inside of the curve. Okay, so that scalar component is f dot n, as we found here. And we want to integrate f dot n along the curve, ds. And as before, as always, we want to transform that ds in the arc length parameterization into something with dt where we can actually compute it. And this is called the flux. So flux is complementary to circulation. Circulation is the total contribution in the direction of the curve. Flux is the total contribution moving from inside to outside the curve. To do this, we'll want to compute that normal vector n. Fortunately, we won't have to take what we did before of t prime over the magnitude of t prime. We won't have to do that because we can use a little trick, and that is to realize that n is orthogonal to both t and the unit vector k in the direction of z. So what we can just do is take the cross product of t and k, and that is the component of t in the direction of y times I minus the component of t in the direction of x times j. You can compute the cross product and you'll get that. The book uses a slightly different notation. In lectures, I have done it like this. I put the ijk at the bottom, but we get the same thing. The two determinants are always the same. Okay, but still, that t, recall that t is r prime over the magnitude of r prime, so that still involves a square root of sum of squares typically. So while this isn't too bad, it'll involve integrating the square root of sum of squares. We don't want to do that. Fortunately, when we convert the ds to an r prime dt, things cancel out very nicely. So we know that the unit tangent vector has components, well, its x component, y component is 0, but its x component is x prime of t over the speed, etc. So n, which is this, as we found over here, is this, which is that. You can pause the video if you like. So our flux integral, n is that. Also ds is this. That is because ds dt is the speed, and the speed is r prime of t. And that means that ds is r prime of t dt. So that's this. And look what happens. Those cancel out. So we wind up with a very nice dot product with no need to compute speeds. And the flux turns out to just be this. So this is a matter of plugging in. If your vector field has components fg and your path has components xy, all you do is you take the integral from a to b over your parameterization of f times y prime minus g times x prime dt. So thank goodness, no need to compute a cross product at all. And this gives the total outward flux across C. Perhaps we should do a concluding example. Okay, so we talked about circulation, and we found the circulation of this vector field around the unit circle and found that it was 2 pi. Let's find the flux of this same vector field across this unit circle. What would you expect it to be intuitively? Hold that in your mind, and let's compute it and see if you're right. So we know that flux is the integral of fy prime minus gx prime dt, where this is our x, that's our y, both of t, and this is our f, that's our g. Okay, and with our parameterization, we're moving from 0 to 2 pi, we're one full revolution. Our f is negative y prime is derivative of sine t is cosine t. Okay, minus x, because that's g, times the derivative of x of t, which is negative sine t. Okay, but we want to get in terms of t only. What do we know? Well, we know that x is cosine of t, and y is sine of t at any given t by our parameterization. This gives our x and y as a function of t. So we have the integral from 0 to 2. Okay, y is sine t, so we have negative sine t times cosine t. We have clarified this slightly if it wasn't clear before. That cosine is the derivative of sine. That negative sine is the derivative of that cosine. Anyway, so negative y is negative sine of t. This is our f, which was negative y, which is negative sine of t. Okay, minus x, which is cosine of t. So now it's a nice Calc 1 integral. We have the integral from 0 to 2 pi of negative sine t cosine t plus sine t cosine t to the double negative. That is the integral from 0 to 2 pi of 0 dt. So we wind up with a flux of 0. That makes geometric sense because for this vector field, there is no contribution of it moving from inside to outside. There is no contribution orthogonal to the curve itself. 100% of this vector field is moving in the direction of the curve. So 100% of it is circulation. None is flux. All of this is circulation. Bring it back to this picture. This is a lot of positive flux and no circulation. This is only circulation, no flux, and other things are in between and have both some circulation and some flux.
Okay, that concludes the 17.2 lecture. Have a great one.